Hello everyone and welcome to the second video of the MECH 220 video series. Today we'll be doing a relative motion problem, which is example 12-231 in the Russell Hiebler 14th edition. So last time we did relative motion with the cables, right? And this time it's a relative motion with anything else basically. And this again will come in handy for any later on problems you'll do with the kinetics, let's say, or even it's common to find a relative motion intermingled with the momentum problems, right? So just before starting, I want to show this picture right here, this figure 12-42 from the book, right here, because it fully helps you grasp what the equation is, right? So here they show the distance vectors are, right? But let's say we have the formula VB is equal to VA plus VB respect to VA. So let me just quickly show you where that comes from, right? So looking at figure 12-42, we have our fixed frame of reference at point O, you have your observer, right? And at A, you have an observer that's moving, and at B, you have another moving point, right? Basically. So from O, you can see that A and B are moving, right? O would basically represent your absolute velocity. O sees A moving and B moving. But now we know, let's say, the velocity of A. We want the velocity of B, right? So VB, which is what the fixed observer O sees. Let me repeat. VB is your absolute velocity, which the fixed observer O sees is going to be VA plus VB with respect to A. And right, that makes sense because if you're looking at A over here, right, O over here, right, O, RB is this vector here, or we could say it's VB. This is the same as VA over here plus VB with respect to A, right? So if we're given VB and VA, we could get VB respect to A. VB respect to A is the relative velocity of B with respect to A. So I hope that helps you understand a bit more. It takes a while to wrap your head around, for sure. So moving back to our problem for today, we have a ship that travels at a constant speed of Vs equals 20 meters per second, and the wind is blowing at a speed of 10 meters per second as shown. Determine the magnitude and direction of the horizontal component of velocity of the smoke coming from the smokestack as it appears to a passenger on the ship, right? So here we're given a diagram which is great with angles and a coordinate system. Here I prefer using vector analysis always because you'll see as you go through the course, you will be using vector analysis more and more. So it's better to get comfortable with it now. And a vector analysis, you don't have to worry about getting the right or wrong sign because it will take into account everything. Whereas in scalar analysis, you have to be more mindful of that, which can get tricky. So let's start solving our problem. So we're given Vs and Vw, and we're given the angles. So the first place to start, I would say, would be to get it into its vector components, right? So vector components. So Vs is the ship, right? If we look at Vs, we're given it's at a 45-degree angle from the horizontal and it's going at 20 meters per second. So breaking that down, we get Vs is equal to 20 cos 45 I plus 20 sine 45 j meters per second, and let's solve that to make it simpler. 14.14 I plus 14.14 J. And this is meters per second. Don't forget the units. And VW, similarly, we're going to do at its 10 meters per second, 30 degrees below the horizontal. We get 10 cos 30 degrees I hat minus 10 sine 30 degrees J hat. Simplifying, it's going to be 8.660 I hat minus 5J meters per second. Okay, so we have Vs and we have Vw in its vector component form. Now we just want the velocity of the smoke coming from the smokestack as it appears to a passenger on the ship. So this is probably the trickiest part of the problem, figuring out what that is, right? The velocity of the smokestack is analogous to our VB respect to A, right? Since VS is it's a translating observer, right? VW is also a translating point. The wind is going to be blowing the smoke, right? The wind is blowing the smoke, which is at VA, basically. VA, if we're looking at our figure there, or in our problem VW, the smoke is being blown at VW. Velocity of the smoke is just the velocity of the wind with respect to the ship. So I'll write that down here. Velocity of smoke is velocity of wind with respect to ship. And that is just velocity with respect to ship. So now that we know that the velocity of the smokestack is just the velocity of the wind with respect to the ship, we can plug it into our relative velocity equation, which for this case is going to be the velocity of the wind is equal to the velocity of the ship plus the velocity of the wind with respect to the ship. Plugging in our Vs and Vw, remember these are vectors, we have 8.660 I minus 5J is equal to 14.14 I plus 14.14 J plus V with respect to S. Remember, these are vectors, that's why they have the underbar. And solving for VW with respect to S, we get negative 5.482 I minus 19.14 J. And this is meters per second. Just making sure the minus 5, it comes from 8.6 minus 14.14. And the minus 19 comes from minus 5 minus 14.14. And now we just want the magnitude and the angle, right? So getting the magnitude, we have a vector, we just want the magnitude. So the magnitude is negative 5.482 square plus minus 19.14 square. And getting the magnitude, we have 19.9 meters per second. I'll just highlight that. And we also want the angle, right? The direction the angle theta makes with the x-axis is just going to be theta equals tan inverse of 19.14 over 5.482. That's going to give us 74 degrees. Which way is that 74 degrees? We know that the VW with respect to S is negative 5 this way in the I direction and negative 19 this way, right? So this was our 19, this was our 5. Tan is opposite over adjacent. This is our theta. So this is our theta here, 74 degrees. And we've solved the problem.